This video is about sparse matrix vector multiplication. A sparse matrix is sparsely populated by non-zeros. Most elements of the matrix are 0, and there are only few elements that are not 0. Dense matrices, on the other hand, are densely populated by non-zeros, so most of the elements are non-zero, and we don't exploit any sparsity. So sparse matrices, they are very helpful because using the sparsity can save you lots of computing time and also memory. You only need to carry out operations for elements that are non-zero, and all the elements that are 0, all those operations you can skip or you can simplify operations. Also, you only need to store the elements that are non-zero. This is an example of a sparse matrix, cage 6. It has 93 rows and columns, 785 elements are non-zero, and we have about 8.4 non-zeros per row. So most of the elements in a row are empty, as you can see. And the density of this matrix, which is thus the number nz, number of non-zeros, divided by n squared, is 9.1%. Multiplying a sparse matrix by a vector is done by taking a dense input vector v, multiplying it by the sparse matrix A, and then we get an output dense vector u. And the ith element of u, ui, is computed as the sum over all the j's of aij, vj. Now when you look at this formula for all the i's, how would you exploit the sparsity of the matrix in this computation? Well, when you've thought about it, you maybe get to an algorithm. What you need to do is exploit the fact that these aij's in most cases are 0. So after initialization of all the ui's to 0, you perform the operation ui plus aij vj only for the elements that are non-zero, for which aij is not equal to 0. And you don't even perform this test because usually you only store the non-zeros in a data structure. That's how you save all the work for the zeros. An important application, traditionally for many years already in scientific computing, is the iterative solution of linear systems or of eigensystems. So linear systems Ax equals b can be solved iteratively by starting with an initial solution, it may be a random solution, and then successively improve this solution until you are satisfied. And the first iterative method for linear systems was the conjugate gradient method, and there are other methods like GMRes, BiCGS-tab, IDRS that are useful and that have been developed over the years. For eigensystems, Ax equals lambda x, there are also methods like the power method, Langshaw's method, Jacobi-Davidson. So there are many methods. All of these methods have at their heart the multiplication by a sparse matrix. That's why sparse matrix vector multiplication is important. There's another killer application for sparse matrix vector multiplication, which is web search by the Google PageRank algorithm. You may wonder, why does this particular web page end up on top? Here I was looking for bulk synchronous parallel, and then you see a Wikipedia page getting on top, and also in Google Scholar some articles. What determines the page that comes on top, your first 10 search results. It's the Google PageRank algorithm, or some refinements that were done later on. And we can view this algorithm and look at the role that the sparse matrix vector multiplication plays in it. So let's define, first of all, the sparse matrix, the matrix that corresponds to the web. So if we have an n by n matrix A defined by a 1 on element aij equals 1, if we have a link from web page j to web page I, and we number all the web pages from 0 to n minus 1, then this defines a sparse matrix, because pages link not to all other pages, but only to a few, maybe on average 10. That's why this matrix is sparse. But it is huge. There will be billions of web pages, and so we have a very large matrix. And now we can define a vector of all ones, call it E, and look at what A times E is. By the definition, by linear algebra, the ith component of AE is just the sum over all j of aij, ej, but these e's are all 1. So this is the sum of j of aij, which is, by the definition of A, just the total number of pages pointing to page I. This already says something about the importance of that page, because if many pages point to you, then you are important. This is how Google started. And so this is a linear algebra notation for the importance of a web page. But we can do a little bit more than that, because not all pages are equal. If some important web page points to you, then that should count as more. So for that, we can, instead of taking A times E, we can take A squared times E. So we multiply, after we have obtained the importance of the web pages, we multiply A again by this vector, and that takes the importance into account when pointing to me. So we can do this again and again until nothing changes anymore. So once we have obtained a steady state, A times x is x, we have converged, and we obtain the vector x, where xi tells you how important page I is. The main operation here is, again, multiplying a sparse matrix with a dense vector. This is an example of a weblink matrix. We started with the BSP Worldwide web page, and we looked at the pages it pointed to, and then the pages to which those pages point, etc. And we limited the search, which was done by a web crawler, to 500 pages. And here you see the result. It's a sparse matrix with a dense block in the middle, which actually is the University of Leuven. And we can multiply this matrix with this initial vector of all ones, and obtain from that what are the important pages. Okay, in this model, we want to take care that if you're not following a link, but just are bored and jump to an arbitrary page, that this is incorporated in our matrix. So this is called the random surfer model. And what we assume, first of all, is that if you have C outgoing links in a page, Cj for page j, then the chances of going to each of those are 1 over Cj. So we divide by that. And to do that in our linear algebra matrix notation, we define a diagonal matrix D, which on the diagonal has all these numbers, how many outgoing links there are. For simplicity, we assume that every page has an outgoing link, which is in practice is not true, but that for simplicity we assume it here. And then there's a certain chance that you follow an outgoing link. Typically in this computation it's 85%, we call that alpha, and 1 minus alpha is the chance that you jump to an arbitrary page. And then the Google matrix has two terms, alpha times A, modified by this matrix D, and we have this random surfing behavior, and this is modeled by a matrix E, which has all ones, and then the chance that you go to one of those pages is just 1 over n. So the page rank of a page is determined by multiplying this G matrix repeatedly with a vector. And just to make sure, the first term is sparse matrix, the second one is actually a dense matrix, but it's never stored because it's a very simple matrix, all ones. Now, another application of sparse matrix vector multiplication is in looking at a molecular dynamics simulation where particles move in a molecular dynamics universe. And here we see a number of particles, and they have short-range interaction. It means if they are close enough, they interact, they exert a force one on the other. If they are far away, they don't interact. And in this case, if we have a radius of a cutoff radius of 0.2, it means that if two particles are closer than 0.2 together, then they interact. Actually, the square here is a 1 by 1 square. If they are farther apart, they don't interact. So if you draw a circle of 0.1 around every particle, then once two circles intersect, it means that their corresponding particles interact. So we can translate this system to a sparse matrix, where every particle I corresponds to row I and column I of the matrix. And if particle I and j interact, then we get a force Fij, which is non-zero, and actually Fji, which is minus Fij, is also non-zero. And particles that do not interact cause a zero. And here you see that for the system that we have, this is a sparse matrix. And what I also show in this picture is not the force matrix F, but F plus I, where I've added the identity matrix to the diagonal. And this represents, this F plus I, the information flow of an algorithm. It's the information that you need to compute a new position of and velocity of a particle I. What you need is all the Fij's that are non-zero, but also the diagonal element, which basically says I need the velocity and the position of myself at a previous time step. So this is the matrix that represents it, and you could use it, for example, to find a good distribution of the particles. You could use this matrix. That's a different look at the particles. Okay, so now we have a sparse matrix. We want to multiply the matrix and the vector, but we need to store the matrix. And for this we have data structures. And I will discuss two structures. One is the simplest possible scheme. It's called the coordinate scheme, or also the triple scheme, where for every non-zero in the matrix you store I, the row index, j, the column index, and the numerical value aij. So we need 3 values for every non-zero, but we don't need to store the zeros. So this is a very convenient and easy to explain data structure. And it's also useful for input and output, even to a parallel machine, because I can send a triple to the parallel computer, send it directly to the processor that's responsible, and it has all the information on the non-zero. But it's a bit difficult to use if you want to do other operations like row-wise operation or column-wise operation, because then you have to search through this bunch of triples, and that may be difficult. So if you have a matrix A in this format and a matrix B in this format, it may not be that easy to add them up. There are other data structures, and a very common data structure is compressed row storage, CRS. And what happens here is that every non-zero is represented by its column index j and its numerical value aij. And all the non-zeros of one row of the matrix, they are stored together. And they are stored, every row is stored after the other. And for this to work, we need to know where a row starts and ends. So we have an array start, which says start I is the index of the address of the first element of row I, the first non-zero of row I. So if you want to know how big row I is, how many non-zeros there are, you just compute start of I plus 1 minus start I. It's the start of the next row minus start I. And for convenience, also to be able to handle the last row, we just define the start of n to be the number of non-zeros of the whole matrix. So this is an example. Here you see a matrix with non-zeros 3, 1, 4, 1, 5, 9, 2. It's the pi matrix, actually. It's a 5 by 5 matrix, 13 non-zeros, 12 zeros. If we store them, we could store the numerical values, 3, 1, 4, 1, 5, 9, etc., in an array A. Then the corresponding column indices, look at the first row. We have a 0 at index 0, and then we have 3 at index 1. So the first column index would be 1, and then the last one in that row, that's index 4, so that gives a 4. So this explains the jk equals 1, 4, etc. And then we go row by row. We also need to say where a row starts. Now, obviously, row 0 starts at 0, but since it has 2 non-zeros, row 1 starts at 2. And then again, we have row 2 starts at 4 because row 1 also has 2 non-zeros, etc. So that's the CRS data structure for the pi matrix. Now we can transform our algorithm for sparse matrix vector multiplication using the data structure. How do we do that? We go row by row, and for every row we just initialize ui, the output element, to 1. And then we go through the elements of the row, so we run the indices from start of I to start of I plus 1 minus 1. And for all of those, we add to ui the numerical value, ak, times the value of v in jk, because jk is the column index, and that tells you where we should find the v value. So this is the formulation for the CRS data structure. To summarize, sparse matrices, they are the rule rather than the exception, because often variables in a computation are connected to only a few others. And that's why not to all others. That's why it's sparse. We have seen that there are many important applications of sparse matrix vector multiplication. SpMV is the abbreviation. One of the most important ones is the Google PageRank algorithm. We've seen the compressed row storage data structure, which is very useful. It collects all the non-zeros of a row and sets a pointer to the start of it. The algorithm is very simple, the SpMV algorithm sequentially, but you will see that it is a very rich and challenging topic for the parallel case. Now a final question to you. Here is again a 5 by 5 matrix, a different one. It actually has an empty first row. Can you formulate the CRS data structure for this matrix? And in general, if you have an n by n matrix with nz non-zeros, how many data words do you need to store the matrix in the CRS format? And we assume that reals and integers, they all take exactly one data word.